In the last video, you learned about acids and bases and what it means to be an acid or a base and what the difference between hydrogen and hydroxide concentrations are. In this video, you're going to learn about how to actually calculate the pH of a very simple solution. In chemistry, you'd go a little more in depth and probably have some pHs that wouldn't be exactly the whole number on the pH scale, but we're going to keep this simple just as an introductory lesson. The basic idea for understanding the pH of a solution is understanding this equation right here. What this means is it says the concentration of, which is what these brackets are, the concentration of hydrogen ions, or sometimes if a textbook does hydronium, hydronium is written as H3O+, but many times I tend to do more just H+. So going back again, the concentration of hydrogen ions multiplied by the concentration of hydroxide ions is always a constant. It is equal to 1.0 times 10 to the negative 14th. That is every single time. So if you ever had two variables, x times y equals a constant answer, then if x goes up, then y must come down. So that's how these two act as a teeter-totter, that if one goes up, the other has to come down. They both can't go up in a solution. So here's an example that I put. I said, question mark being the variable, multiplied by the concentration of hydroxide. If I said the concentration was 1.0 times 10 to the negative first, the constant answer or product is always 1.0 times 10 to the negative 14th. So algebraically, to solve for this, we're going to isolate the variable by dividing both sides by 1.0 times 10 to the negative first. So this would have been 1.0 times 10 to the negative 14th divided by 1.0 times 10 to the negative first. And that answer is 1.0 times 10 to the negative 13th. If you would like to try this in your calculator, my suggestion is to learn the appropriate keys on your calculator that could do this math for you. So what you would do is you would type 1.0. Instead of typing multiply by 10, there is a button that has a capital E, capital E. That will take the place of times 10. So from that point on, you can write 1.0, hit that button, the capital E button, sometimes it's a second function button, and then type in negative, not a minus sign, negative, which is sometimes on the keypad, specifically by the numbers, 14. And then you would do the same thing. You divide it by 1.0, the EE button, then this time type negative 1, and see what your calculator would give you. If you can't get 1.0 times 10 to the negative 13th, then you're not understanding your calculator, and you've got to do something, whether you come to me specifically and say, how does my calculator specifically work, or read the owner's manual. But what will happen is, this answer will be 1.0 times 10 to the negative 13th. Let's try another example, a verbal example not written down, but say that I had the hydrogen concentration was 1.0 times 10 to the negative 8th. If I did the same thing, I take 1.0 times 10 to the negative 14th and divide it by what my given value would be for hydrogen, which I said was 1.0 times 10 to the negative 8th. You can try that in your calculator, press pause. I'll tell you the answer in a second. But what you would get is 1.0 times 10 to the negative 6th. So hopefully after two examples you see a very simple way to do this. As long as the base number is 1.0, which is what the case will be for every pH problem I give you in my class, all you have to do is technically subtract the exponents. So negative 14 minus a minus 1 was negative 13. In the second example that I just verbally explained, where this was negative 8, I believe, 1.0 times 10 to the negative 14th divided by 1.0 times 10 to the negative 8th, you subtract negative 14 from negative 8, and that would have given you your 1.0 times 10 to the negative 6th. So you don't really need to know your calculator, but in future, when this number changes, you will not be able to do the math as simply. I keep it simple by having the same 1.0 in front of all of the numbers. It's imperative to be able to calculate the different variables. If I give you hydroxide, you have to be able to get the hydrogen. If I give you hydrogen, you have to be able to get to the hydroxide. That's the first part of calculating pH. Once you have determined the hydrogen concentration, that is the concentration you use. So if you're lucky and I give you the hydrogen concentration immediately, then you can go right to the next step. But if I give you the hydroxide concentration, just like we had to do in this example, you have to get to this value. So it might be an extra mathematical operation to get there. But the way that you do this, To calculate pH, it is a simple equation. You take the negative log. You don't have to understand log in order to do this math. The calculator will do it, but once again, I'm going to show you how the calculator really isn't even needed for the simple examples that we work with. You take the negative log of the concentration of hydrogen. Because pH stands for power of hydrogen, we're working with what is the pH of this solution, so we work with the hydrogen concentration. That's why if I give you hydroxide, you just can't plug that value in. You would not be calculating the pH. You'd be calculating the power of the hydroxide, which itself is a calculation, but we're not working with that. So if you plug into your calculator negative, press the log button, which again is its own function, and then plug in 1.0, you press the EE button, negative 13, your calculator will determine that the pH is 13. So if I did another example, for the example I said, say that the pH or the hydrogen concentration was 1.0 times 10 to the negative 8th. If I plug in negative log of 1.0 times 10 to the negative 8th, the pH is going to be 8. So you can see very simply that really the calculator is not needed. All I need to do is, as long as this is 1.0, that's the only time it works like this, and that's going to be every time in my class, again, it will be 1.0. All you're going to have to do is take the exponent associated with it and turn it into a positive whole number, and that's your pH. So here is a list of basically what you would eventually get to. You can memorize this or realize very quickly that 1.0 times 10 to the negative first, the pH is 1. And you can see all that happens from that point on is the exponent and the pH correlate. So what we'll do is look at these concentrations compared to the pH. So many people, I'm not sure if you truly understand what the scientific notation is of these, so I will type out kind of over here what this represents in decimals. So this first one, 1.0 times 10 to the negative first, equates to 0.1. This next one, 1.0 times 10 to the negative second, that is 0.01. So what is happening between the concentrations? The power of hydrogen, which is what the pH scale is, from the other video you learned that this is the most powerful acid, pH of 1. Let's look at the concentration, 0.1. How does that compare to 0.01? This is a larger number. This will be the largest number for the power of hydrogen, so that's what corresponds to the pH of the solution. The most powerful or highest number for hydrogen ions is going to equate to the most powerful pH solution or most acidic solution. The difference between these two values, I often look at it in terms of the pH of 1 is how much more concentrated or how much stronger than the pH of 2. 0.01 to 0.1 is a 10 times difference. So what I can say is that on the scale of pH, the difference of 1 pH going from 2 to 1 is actually a concentration difference of 10 times. So I would say that a pH of 2 is 10 times weaker in concentration than a pH of 1, or I can say that a pH of 1 is 10 times stronger than a pH of 2. It's kind of your perspective of how you want to look at it. Then if we go down to the third one, I'm not going to do this for each of them. Hopefully quickly you'll get the understanding. 0.001 is the concentration of 1.0 times 10 negative third. So look at the difference. The pH difference of one scale, 3 to 2, is still only a power of 10. But if we jump from 3 up to 1, that is a difference of 100. So a pH of 1 is 100 times concentrated than a pH of 3. But in the pH scale, again, it's only a pH of 2. So it's very much like the metric system where prefixes were, if you were right next to it, it was a 10 times difference. If you were 2 away from it, it was a 100 times difference. So if you look at this example, what is the difference in value between the concentration at pH of 2 versus the concentration of hydrogen at pH of 3? So the best way to word this answer, I would say, is that the pH of 2 has a 10 times stronger concentration of hydrogen than a pH of 3. Sorry about that. The difference in concentration of pH of 2 versus 4 is that a pH of 2 has 100 times more concentration of hydrogen than a pH of 4. Instead of just writing 10 times or 100 times, you give the perspective of greater or less than in that answer. Looking back at this, what will happen is sometimes the hydrogen concentration or hydroxide concentration might be given. If you look at the hydroxide concentration, as this is going down, again, this is getting weaker. From the beginning of this, the equation says as one gets lower, the other must go higher. So as we look at this, 1.0 times 10 negative 14th is actually a very, very weak acid. Look at that number. I'm not going to type it in terms of what it looks at a decimal place, but that's point with 13 zeros and 1, much, much smaller. So it's a very minuscule number compared to 0.1. So if we look at it like this value right here, a pH of 13 is a very basic, very strong base. That means the hydrogen concentration at 1.0 times 10 negative 13th means the hydroxide is 1.0 times 10 to the negative first. So we've flip-flopped. A very weak number here for concentration of hydrogen gives a very strong number for hydroxide. So again, verbally speaking, this is a 0.1 concentration of hydroxide. So the difference between these two, if this is the hydroxide, you have gotten to be a very strong value here. So what we'll do is recognize the fact that if you increase the concentration of hydrogen ions, what that does, okay, that lowers the pH. So think of it. Increase the power of hydrogen or the concentration, you're going to get a stronger acid. Then that's a lower pH value. If you increase the concentration, sorry, it's really early learning right now, of OH, then what that's going to do, it's going to increase the pH. So this goes hand in hand. You increase hydroxide, you increase the pH. Think of that. If you increase the hydroxide, then you're making it a stronger base, and that's going to be a larger number on the pH scale. If you decrease the concentration of hydrogen ions, what are you going to do? Think about that. You will increase the pH, and if you decrease the concentration of OH, you decrease the pH. So the hydrogen concentrations, they do opposites. The change in hydroxide causes it to go with the pH. Right? So that's how you calculate pH. If you have any further questions, you can let me know. The last term on the notes is a buffer. And we'll talk in a lab about specifically a buffer in more detail, but by definition, a buffer is a solution that resists change in pH. So what will happen is if you put an acid into this solution, it will maintain its original pH value. And we'll talk about why they're useful and how your body has them.